Hey everybody. So today we're going to look at our meter stick drop lab, this lab right here that you guys should have gotten. Obviously a lot of you guys probably won't have a meter stick. Okay, so here's our meter stick if you ever see one. And a meter stick, we use centimeters and meters. So you see starting at 1 and going all the way to 100. Okay, and 100's not on here because the very tip of it's 100. Okay. If you don't have one of these, just use like a broomstick or something like that, something that's pretty straight that you can use at home that's about the length of this. Maybe you can get a ruler out and, kind of measure it off with the centimeters, 1, 2, 3, 4. I know you'll have to do it 100 times, but, we kind of got to do what we got to do. But anyways, so it's pretty self-explanatory. I know you guys probably already started it. That's why I didn't do a video on it. Is all you have to do is have a partner, your mom, your dad, a brother or sister, just drop it. And so obviously if it's by sight, you're looking at it and they drop it randomly and you catch it. And then you just read 23 centimeters is what this says here. That's your reaction time, okay? And you'll do that 5 times in a row just for your sight, okay? And so obviously that is for your first table up top here, and you're going to do that 5 different times, okay? And then you're going to find the average for that. And you're going to write the average right here next to my finger where it says ABG, which stands for average. Okay, then you'll do the same thing for sound, and maybe you'll look away from it, you'll close your eyes, and you'll have your partner randomly drop it, and at the same time and it has to be pretty close to exact the same time that they drop it, that they say go, or they say drop, or something like that, okay? But you're not looking at it, and that's how you use your hearing, okay? And you'll do that 5 different times. And again, you'll come down here and do that, do your raw data. You say it 5 times, and then you add those up and find your average, okay? So just to be clear on how to find average, we have to add up our trials, okay? So you add up your numbers 5 times, your 5 different numbers, and then you'll take the sum of those 5, and then you'll divide it by 5. Okay, that's how you find your average. Sometimes on your calculator, we've been having problems in this in class. Kids will be typing it into their calculator, and so they'll type like 25 plus 30 plus 31 plus 32 plus 36. Okay, and they'll get all these, but then they'll just divide by 5. Okay, in your calculator will then take 36 divided by 5. And then it'll add 32, 31, 30, and 25 on top of that. And we don't want that, okay? First, we want to add all of your numbers, all of your readings that you had, and then you'll take the sum, right? That's the sum is when you add them all together, and then you'll divide the sum by 5. That's what we want. Okay, so that's how you get the average, just in case you have a little trouble with that. So essentially, your average should never be bigger than your largest number, and will never be lower or smaller than your lowest number. Okay. All right. So then, once you find that, today we made a graph for everybody, and we did this in your notebook. So I encourage you. You need to get a notebook out right now. Okay, so if you need to pause the video for a second, get your notebook out, get a pencil out, get a pen out. I'd use a pencil. But anyways, so a way that we like to, in the scientist world, to display numbers and things like that, because sometimes you'll do some experiments that have a lot of numbers. And if I'm looking at 100 different numbers in this lab write-up, I can't visualize or I can't really see what that stuff means. So we use graphs to show that, okay? And I realize we only have 2, right? We have our averages are what we're going to use. We're going to use our sight average and we're going to use our hearing average. So that's not too hard to visualize really, but when you get into more complex ones, they get a little more complex, I guess. All right, so when we draw this, our graph right here, okay, we have our graph and we have 2 axes. We have our vertical and we have our horizontal, also known as our x-axis and our y-axis, okay? This is in math as well. Okay, so our vertical one is the y, and so the best way to remember that is y is to the sky, and then the x is just the other one. I don't have a good way to memorize the x, okay? And so we have some other things that we need to do. We have to label our axes, okay? So what are they going to be exactly? What are we going to call them? We need a title. Okay, so what's our title going to be? We decided on sight versus hearing reaction time. So you could write sight versus hearing reaction time, okay? And that's just like a book title. And then we'll have our axis titles. And so we have to put our readings in a very specific place, okay? So we have our independent variable down here. And then we have our dependent up here. Okay? And so what are these? What are these? And you guys may have done this before, but our independent variable, okay? This is what the scientist manipulates. Okay, so scientist manipulates. The experimenter, right? So we're the scientists in this case. The scientist manipulates that, or another word for manipulate means to change, or we control that, okay? This is often what's being tested, okay? So we want to test our hearing and our sight. So our hearing and our sight would go down here at our independent variables. So we're going to make a bar graph, by the way. So there's bar graphs, there's scatter plots, there's line graphs, and we'll go on into that stuff as we go through the year and make more graphs as we do more experiments. So we have our sound, right? And we have our sight. Let's talk about dependent variables. Dependent variables. Okay, so these are also known as our responding variables. Okay, they are dependent on the independent variable. Okay, so in this example, our reaction time is dependent upon our sense, our hearing or our sight sense. Okay, so this is our, what did I say here? What's being measured, right? You also see this as the responding variable. Okay. And you guys can see all of that. Great. Okay. And so over here we have our reaction time. Okay. So this is our actual label. So in a real graph that you would turn into me, you wouldn't actually write independent down here. You wouldn't actually write dependent. You wouldn't actually write title. Okay. You would actually put a real title up here. Sight versus sound, reaction time. You would actually put sound, sight. You would actually put reaction time. And what do we measure our reaction time in? We don't actually use time, right? What did we use? We used a meter stick, and then we measured how far it dropped. And so we're actually measuring it in distance. Okay, so that's how we're doing this experiment. And a lot of times that's what we have to do is we have to be creative on how we're able to react. Okay, so we're not actually using times in seconds or minutes this time. We're using centimeters, and so I will abbreviate centimeters with cm there. And we usually, whenever we measure them, we don't underline it, sorry. We put them in parentheses, okay? So now we got our axis titles up, and you don't need the y and the x if you're ever turning something in for me, okay? Next, we need some numbers, okay? And so how do I know what number to end with? I always have to start with 0. Okay, but then how do I know where to stop? Well, I know that my meter stick goes up to 100, but you really only need to go to your highest number that you'll have. So look at your sight and look at your sound or your hearing average. So which one of those is higher? So let's say your hearing maybe was the largest reaction time, so that means it's the slowest reaction time. So let's say if the average of that was 35, we would actually want to go slightly above 35, maybe 40. Okay, so we want to be able to fit all of our data on our graph but we don't want to have to max it out at the very tip top of our graph. We want it to fit on our graph comfortably. It has to be kind of pleasing to the eye and things like that, so it's easier to read. So it doesn't look like we ran out of room at the very end. You know what I mean? So let's say that, like I said, my highest reaction time was 35. So I'll choose 40. It could be 60 for you. It could have been 70 for you. It could have been a lot higher. It could have been a lot shorter. There was a lot of kids who had like 10 centimeters, or there was a couple who had an average of like 4.6 centimeters and things like that, and that's totally fine. There's a wide variety in our class. Okay, so you use what numbers you think would work best. I'm going to use, if my average was 35, I'm going to use 40 because I feel like 40 is a even number, so that's important because it's good to have to do these in good increments. When I start making my little tick marks here, right, and I make my increments, 40 is an even number where I can divide easily in. Like I could go in 5 centimeter increments, I could go in 10 centimeter increments, but I'm going to go for 5, okay? And normally when I do this, you guys have line paper. Hopefully you're using a notebook paper. It'd probably be helpful if you use maybe a ruler and you spread those increments out evenly, okay? And so I don't have my first 5 increments is this big, but then my second 5 increments is this big, and then our graph is off, right? It doesn't look the best. But for now, I'm just going to kind of freehand it. Okay, so if I'm going at the top, my max is 40 centimeters. Okay, I start at 0 down here. So I just do my 5, 10, 15, 20, 25, 30. see what I did here? 35. And let's go ahead and bring this all the way down here to 40. Okay, so that's why it's good to use. If I redid it and everything, I would have spread it out a little more and made it look a little nicer, and I would have made these increments a little wider so my graph would have looked a little more neat. Okay, but here I go 5, 10, 15, 20, 25, 30, 35, 40. Okay, and what I say my sound here would have been 35 centimeters was my average, right? I'm not putting my individual 5 trials data in here. That's called raw data, and we don't really include that stuff. We use summary or summative, and that's what the average is. It includes all of this raw data, so the person who's studying this, they don't have to sift through all of the raw data. That you just give them the summative data of what it means, okay? And so we have our 35. I find 35 here. Make a nice bar here. Might fill it in a little bit, okay? And then let's say maybe my site was 24.5. So I go up here 5, 10, 15, 20, 25. And when I say 24.5, I'll come over to 25. I know it's a little lower. So 24.5 is a little lower, so I'll come just below 25. And I know I'm just kind of eyeballing it right now. Again, if I had a ruler and I had a nice loose leaf paper, or we'll get into the year, we'll actually start using things like Excel or Word documents that you can punch the numbers in, and we can make a nice looking graph. But for now, we're going to be doing hand style. And so I like using different patterns just so we can differentiate between the two. And we don't really have to. It's just something I like to do. But since we already have this bar labeled for sound and this bar labeled for sight, you could put them up as the same color and have the same pattern on them. That's fine. Sometimes scientists will use something called a key, or they'll use a legend, okay? And that's for if the author of the experiment, they didn't have sight and sound down here. And so what they would do is this one was sight, and so they would have, right, up here polka dots, and this is sight. That's our key. And I know I'm running into this other stuff. And that pattern and color means sound. Okay, and that's a key. But if you have a key, you don't need to label it down here. If you don't have a key, then you should label the bars individually. And the reason why maybe you want to do that is if I have 10 different bars where I have 10 different independent variables, it might get a little cluttered down here trying to write them all out. You know, your words are too long and you can't fit it all down here. So maybe it'd be easier for you to write it out to the side where it's easier to do that and it looks a little more cleaner. It looks more neat, right? Because we want this to be neat. I want somebody who doesn't know what I'm doing. I want them to be able to walk in from the outside and look at my graph and be able to see what I all got here. And they're able to see, oh, you're measuring the reaction time. I see that you have reaction time over here. You measure that in centimeters. And what's your senses that you're measuring? Oh, you're using sight and sound. Okay, and this one stands for sound. This one stands for sight. Okay, so we have to make it nice and organized. All right, and I think that's where we stopped right there. And so we use this data as evidence. Okay, so when you start doing your questions at the end of this lab, okay, you want to use this as your evidence. So what I say this was 35, and I said this was 24.5. Okay, you want to use these actual pieces of evidence when you're writing your responses, like, was your hypothesis proven or disproven? That's what it says in your lab. Let's change that. Okay, so I already told the class today, we're going to cross out prove and disprove. That's on number 3, and we're going to just say supported or not supported. Okay, because nothing's actually right or wrong, right? In science, everything can tend to change, and that's kind of, as scientists, we believe that nothing is set in stone. Everything's subject to change. Okay, so that's why we say we have evidence, and just like in the legal system, you use evidence to support or not support something so it's not that your hypothesis was proven or disproven. It was, do you have the evidence to support your hypothesis? And if you don't have evidence to support it, then your hypothesis is just not supported. So it's not like you got it wrong. Okay, so if you're doing this and your hypothesis was wrong, that's fine. I'm not taking off for that. You're just doing good science, right? You thought wrong, but you're not wrong. I mean, you did good science. And if you're looking at your data, right, if I said that my sound would be faster in my reaction time, but my evidence here obviously doesn't reflect that because it took me longer, right? With the bigger number, that means it took me longer to catch that meter stick. And so obviously then my reaction time, I have evidence that shows my reaction time for sound is slower and my sight reaction is faster. So in my hypothesis, it would have been not supported. Okay. So anyways, anytime it's asking you to look back in your lab and discuss it, and you want to try to prove or support something, always point back to, what did you find in your lab? Okay. What was your evidence? And use good hard numbers like we did here. Okay. The summative ones. All right. So then we moved on we went to the computer lab, and we started on our Glencoe virtual lab, that's Ways of Scientists. Some of you might have done this one already, the strange case of beriberi and the discovery of penicillin. If you did that, that's fine. We just didn't get to it today. I'm trying to find that how to do science lab. So that's the one with the color. Okay. So what that one's asking for is, how does color affect? So this is number 1. I asked you the question. What's the question for this lab? It's, how does color affect heat absorption? Okay, so it's asking, essentially, does black, blue, yellow, white, and green, which one absorbs heat the best? And so you have to read that first page where it gives you a background on what is light. Is light absorbed by different colors? If it's absorbed more, that means it gives off heat and things like that. So you're going to measure the temperature of all of that stuff. Okay, so you need to come up with the question, you need to do 1, and you need to do 2 before you start doing the lab, okay? You needed to, and then number 2 is asking about the hypothesis. So write a good hypothesis. If this color, and so fill in that, what color do you think? If this color is the hottest, then it must absorb the most color, okay? Something along those lines. You could change it up, do something like that. But you have to come up with a little bit of reasoning when you do a hypothesis. It's not a guess, okay? Because you read your background to this and what light does with color and gives off heat, you have somewhat of an educated knowledge of light now and heat, and you need to use some of that reasoning that goes along with that hypothesis, okay? And so then you'll go and you'll start with like wool, okay? And you'll measure all the temperatures of the wool. So you get 3 temperatures. There's 3 jackets. It's like 30.1, 30.1, 29.8 or something like that. You add all those up, and then you get the average of those 3. So you add all those numbers, get the sum, divide the sum by 3, just like we did in this lab, except we did it by 5 because there's 5 trials. Here, there's only 3 jackets, so 3 trials. Divide that by 3, that will give you your average, okay? And sometimes it'll be like, there was one that was 29.6 or 766, 6 repeating or something like that. I just want you guys to round to the nearest 10th place. And the 10th place, okay, is if it's 1.0, the decimal place behind the decimal, or the placeholder, this is the 10th place. Oh man, I don't know how to write. Okay, so if it's 29.06, I'll round to this guy, and this is above 5, right? So in effect, you'll write down 29.1. And you'll write that down in the box for whatever color you did. So you'll do all wool first, then you'll do all of nylon, and then you'll do all of the denim. And then you'll go through and you'll start answering those questions. And remember, as you're answering those questions, point back to your data. Okay, say I got these numbers. This was the number I got. This is why I think my hypothesis was supported. This is why I think it was not supported, because I have these numbers that are showing this. Be specific. Okay, you don't have to write a whole paragraph. It's possible to be specific and concise and not have to write a whole bunch. Okay, the more concise you are, actually, the less you have to write. Okay, hope this video helped. If you guys need any more questions and things like that, please email me. But other than that, have a good one, everybody.